density regions and low density regions. We will now obtain a mathematical equation for the speed of transverse vibrations of a stretched string. What is the meaning, the speed of transverse vibrations of a stretched string? If I have a string stretched like this, if I set it into vibration by plucking it one end, by creating a transverse vibration, what is the speed with which the energy gets transmitted along the string? Now, when a stretched string is plucked, the transverse vibrations so produced are propagated through the length of the string like this. You have a stretched string and I pluck it at one end or create a pulse. The pulse will move along the length of the string, and we will look at the speed of propagation. The speed of propagation depends on what factors? There are two main factors on which the speed will depend. I want you to understand both these. It will depend on the mass per unit length. Mass per unit length. In other words, it indicates how thick the wire is. If the mass per unit length is large, it will be a thick wire. And if the mass per unit length is small, it will be a thin wire. Alright, can you make a guess? Which of the wire is more efficient in transmitting energy through it? Or in which of these mediums will the energy travel faster? A thick wire, a thick string, or a thin string? I'm going to leave it for you to think about it. Okay. Now what we're going to do is we're going to take a small segment of the string of length I'm going to call delta S. You see, I have just created a pulse. Now this is the pulse of length delta S. Consider a pulse of length delta S and radius r. In other words, this delta S is actually part of a circle, and the radius of that circle is this r. T is the tension on the string. What is the meaning of T is the tension? Well, it means the force of stretch. The force of tension is the force of stretch. And mu is the mass per unit length. Well, actually, in the last slide, I forgot to tell you that the speed also depends on how taut the wire is, how strongly the wire is stretched. Okay, so T is the tension. Now this is the tension force represented by the arrow. This is the tension force. That is, you can see when the wire is stretched upward, these tension forces try to pull the wire back. Is that right? So this is the tension force, and that is the tension force on either side. When the pulse is in the form of an arc of a circle, it experiences a centripetal acceleration. You see, the tension force is actually a centripetal force, and it pulls the segment back. It experiences a centripetal acceleration, which is supplied by the vertical components of the tension force. You see, this tension does two things. This tension pulls the wire sideways and also pulls this segment downward. The acceleration, the centripetal acceleration, is provided by the component of this tension that is downward. So, first of all, let's mark the components of the force. Now, this tension has a downward component which is T sine theta by 2. If you know some geometry, now this is our segment of length delta S. The angle it subtends at the center is theta. If you now draw a tangent to that segment, the angle it will make with that tension force, which is tangent to that, will be half of this angle. That's a geometry lesson. So if this angle is half of theta, then this component will be t sine theta by 2, and the component that stretches the string, pull the string to the left, will be t cos theta by 2. I hope you understand. We did a lot of these in physics 1. This tension force T has a component t sine theta by 2, try to pull it down, and t cos theta by 2, trying to pull it to the left. Similarly, there is a t sine theta by 2 on the right and a t cos theta by 2. Now if you notice, these two are opposite to each other, they cancel. This t cos theta by 2 will cancel with this t cos theta by 2. That means the only two surviving components are the t sine theta by 2. The vertical component of t on each side is t sine theta by 2, where theta is the angle subtended by this pulse at the center. Now, the total centripetal force, remember, it is the component of the force pulling the delta S down that provides the centripetal force. So what is the total centripetal force? It is this plus this. That will be 2t sine theta by 2. I hope you understand. It is the sum of these two vertical components that gives the centripetal force. So the total centripetal force is 2t sine theta by 2. Do you remember the equation for centripetal force? If an object of mass m moves with a speed v along a circle, what is the measure of the centripetal force? I will come back and ask you that again. Now here I'm going to take a small approximation. When the angle theta is very small, sine theta by 2 can be approximated as theta by 2. You remember we did this in our first lesson also. When the angle is small, sine of an angle is approximately equal to angle itself. Remember, the angle is measured in radians. So we will replace the sine theta by 2 by theta by 2. That means the centripetal force now is 2t multiplied by theta by 2. What is 2t multiplied by theta by 2? That will be t theta. The 2's will cancel. Now, well, I had asked you this question. The centripetal force on an object of mass m moving with a speed v in a circle of radius r is mv squared over r. I hope you remember that equation. So what we're going to do is we take this quantity and equate it to this. Alright? So what is m here? M is the mass of that string. You see? And you know, the delta S is the length of that string. Its mass per unit length is mu. You remember we call it mu, the Greek letter, mass per unit length. If you multiply the length of the string with mass per unit length, you will get the total mass of the string. So mass of the string m equal to mu times delta S. Well, what does mu stands for? Mu is the mass per unit length. So mass per unit length multiplied by the length will give you the mass. And theta, well, you know, I have actually used many results here which I expect you to know. The arc of a circle, delta S is the arc of a circle. And the length of the arc will be radius multiplied by the angle theta. You see, this result is very important for you. The arc of a circle subtending an angle theta at the center, this is delta S. This is the radius r. So we get delta S equal to r times theta. Therefore, theta equal to delta S divided by r. So we're going to say theta equal to delta S divided by r. And let's use all those in there and form the equation. That gives me mv squared over r equal to t theta. And I'm going to replace my m by what? M equal to mu times delta s times v squared over r equal to t times theta. And what is theta equal to? Theta equal to delta s divided by r. Now look at the beauty of this relation. R on the right and R on the left will cancel. Delta S and delta S will cancel from both sides. That gives me V squared equal to T divided by mu. Right? After cancelling delta S over R from both sides and dividing by mu, I get V squared equal to T divided by mu, or V equal to square root of T over mu, where T is the tension, the force stretching the string, and mu is the mass per unit length of the string. A very important relation. Speed of transverse wave on a stretched string is given by V equal to square root of T over mu. Don't forget that.